So we have been talking about vectors, but our vectors just there on top of our space of locations, the Euclidean space with possibly Cartesian system attached to it. Okay, so that is the where we live. Okay, so but now a little bit an overview of functions.
This screen is
functions. Okay, functions. So functions, and once dimensions go up, possibly there are so many options for functions then. And a function is, as you remember, at its most general, is just input-output machine. So f, and then something comes out, something comes in, and something else comes out. So in and out. Okay, and then so the nature of those two entities might vary wildly, and we're just expanding it from numbers to points in multidimensional spaces. Okay, so starting, it could be R and here, R and there. To begin with, we'll start with 1, 2 only. Okay, dimension of the input might be 1 or 2, dimension of output 1 or 2 to begin with. So let me make a little plot here to illustrate what's going on. So I put n's here and m's there, 1 and 2, 1 and 2. Okay, so one dimension, input is 1, output is 1. What is that? What is that? R1 and R1, what are we talking about?
Just normal everyday functions.
Yeah, it's just, the functions of L equals 1, let's say, because now we certainly not going to stop here. Okay, n equal 1, m equal 1, so let me just illustrate it with a little picture. So x, y, and you have a graph. Y equal f of x, so that's calc 1. Okay, so furthermore, there are 3 cells left. And this top left cell is input 1, output 2, dimension input 1, it is a number, output 2 is a location, dimension 2 is on the plane. So this is what? Input is a number, output is a location on the plane. It's a function, see, so the output varies. I'm sorry, input is varies, which makes output vary too. So there's a bunch of values for the input, and then you have a bunch of values for the output, except the outputs this time are points on the plane. So they connect into what?
Surface?
No, a curve, a parametric curve. A parametric curve. So as you can see, that's what I'm talking about. Like this. So there's an x. X's are still there, x and y, but this time there's a third parameter, t. Say t equals 0 here, t equals 1 there. Okay, and this is a parametric curve. So it is a parametric curve, but we put it in a kind of a bigger, wider setting, or so to see the bigger picture. So it is, everything is a function, and they might seem different. And but really they're part of something bigger, and all that we allow to vary right now is just the dimension of the input and output. Okay, so when the dimension of the input is 1, which it means that the input is a number. You can think of it as a parameter, you can think of it as time, and then but there is so much more room for outputs. Okay, it's the whole plane, and since the input is 1 dimension, output is 2 dimension, there is so much room left. Okay, so you're left with a curve, and then there's a bunch of room left out. Okay, so this is just illustrations. And we're going to be talking about that, but let's have one more cell here. Input is 2, location on the plane. Output is a number. So what does it produce?
Curve.
No, this will be surface.
Oh, a surface.
Surface. Yeah. Okay, so there are x's, and then well, the graph of the function is surface. So what is being depicted? Remember that this is the graph and that is the graph. That one is not the graph. That is the path or trajectory of the parameter curve. So the one of the dimension is missing. So 1 and 1, 2. 2 and 1, 3, that's a 3-dimensional space. And over there it's missing, 1 dimension is missing, so we usually illustrate parameter curves with only 2 dimensions, ignoring the dimension of the parameter. So that's just the way it works. So the result is the surfaces, and this is a function of 2 variables. Okay? And then this is what if the input is 2-dimensional and the output is 2-dimensional too. That might vary depending on whether we want to think in terms of points or we want to think in terms of vectors. So, but you certainly can imagine that we talked about that a little bit. If the input is a point, output is a vector, then it gives you a direction every point. You could attach a vector to every point on the plane, and that could be thought of as it's called a vector field, and you can think about motion of a flow of liquid on the plane and a similar thing. So that will be the last one. To proceed, we'll go 1, 2, and then 3. Okay, so the point of we already have had enough parameter curves to appreciate the idea, but now we want to use vectors, or rather multidimensional spaces and vectors, in order to represent parameter curves more efficiently. And you can see already, you have seen how we make all our notation so much more compact when we do vectors rather than doing this. You just say, well, that's a vector. Okay, same with location, certainly. Okay, so you move from multiple dimensions, you move to just one letter. Okay, so that's what we're going to do. So parameter curve is parameter curve is a function of real variable with values in real variable, meaning that the domain of the function is inside of R, just as usual, always with the calculus 1, and the values in R2 or higher. So R3 and or higher. All of these are possible, but let's just do 2-dimensionals. 2-dimensionals, and then we'll see how if you use that's the thing, if you use the right notation, then you're gonna, in dimension 2, okay, and then you use the right vector notation, then whatever you get, it will be fully applicable to the rest of the all the multidimensional spaces. So the simplest curve is, what's the simplest curve? No, there's a simple one. A line, yes, a straight line. A straight line is the simplest one, and that's what we want to represent. So we on the xy plane, and we take a line, and we want to represent it as a parameter curve. Okay, so there is nothing new about that. In fact, it is very familiar because we already have many ways to, just 2 ways to represent them. As before, y equal mx plus b, that is the traditional way to represent it. What is the problem with this representation? A curve, a straight line on the plane written as y equal mx plus b. What's the problem with it?
We're giving the dependence between x and y and not x and y in terms of the third variable.
Yeah, well, yeah, that ultimately I want a parametric curve. This is not a parametric curve, so that's the deficiency. But there's a kind of a more very basic deficiency. Something is missing.
See?
No, something is missing. What I'm saying is just not every straight line can be represented this way.
Is it because we don't have like a t to factor them through?
No. Vertical lines cannot be represented this way. So this is yes, and that is no. Vertical lines are out. Which is when you just working with functions, that is natural. You represent whatever the curve you have with the graph of a function. More likely vice versa. You have a function, you represent it as a graph, vertical line not the graph, so you don't have a graph and you don't have to worry about it. But now we're talking about xy plane being literally a plane, playing ground, if you like, and we'll be moving in all directions that you can think of. So there are no preferred directions. There are no possibility of excluding any particular direction, any particular straight line. So that is unacceptable then, because like I said, some of the curves will be omitted. Okay, so there you might remember there is a different representation that does include vertical lines.
In terms of vectors?
Yes, x and y, no, not parametric. So I'm just reviewing all their stuff. How do we present a straight line so that vertical lines are also included? No?
Can we just we consider scalings of the vector 0, 1?
No, I hope you remember because I don't want to. I'm just about to start with the vectors, but right now, what you might remember from before calculus, it's simply ax plus by is equal to c. Okay, so that is a straight line. Every straight line, including the vertical line, can be represented this way. And if it is possible, it includes all the lines, including those y equal mx plus b. M is simply, what is it? Is a divided by b. If b is not equal to 0. Okay, so if b is not equal to 0, you can get this way. When b is not equal to 0. When b is equal to 0, then you have a vertical line. Vertical line. Ax is equal to c, x is equal to c over a. Well, a presumably is not equal to 0. So one or the other should not be equal to 0. Either a is not equal to 0 or b is not equal to 0. If both of them are equal to 0, we're not getting any line. Okay, so we exclude that possibility. But if a is not equal to 0 and b is not equal to 0, we have the usual representation. We just can it'll make this little step and we have that representation. Or if, like I said, b is equal to 0, then we have a vertical line. So we have everything. And just to refresh your memory, we are not really trying to do that. We're trying to represent it as a parametric curve, and we just should be able to recover this formula at some point. And then besides, that's a very nice formula that becomes more helpful as we move to the next dimension, and that will be the plane. The plane is formula for the plane is similar. Okay, so straight line. Let me pick a specific one, and let's just go through these. Okay, so let's say I start at the point 1, 2. We're going to do it in the manner that it does not really refer to calculus 1 as much, but more the way Newton did it himself. So to understand, to represent the curves, turns out that it's nice to think of them as as if you're moving through them. And so that is where the third parameter comes from. And then he turns around and then uses what he have learned about mathematics or the curves to study motion. But right now we're using the motion as a metaphor, as a starting point to understand what's going on. So then how I could describe line in terms of motion is starts at point 1, 2, and goes in the direction I'll say 2, 3. Okay. So we're using locations, multidimensional locations, using the notation in circular parentheses, and then we use the vector notation in order to indicate which way we're going to go from that point. Okay, so roughly, it doesn't look unfamiliar, I hope. So a 2, 3 from this point. Let's say this is point P, and this is vector B. Okay, so from this point P over here, we are moving in the direction we make 2 steps to the right and 3 steps up. Okay, like this, and 3 steps up. Okay, so that's where my vector goes. Okay, so there's a very simple description of motion. There are no forces involved. It's pure motion along a straight line. You know where you're starting. You know where you're gonna end. It's not very hard to imagine what the curve is going to look like. That's what it's going to look like. The rest of the curve. And indeed, it is. In fact, it suffices to have 2 points to determine any straight line. That's what we know from Euclidean geometry. And now we just want to do represent it algebraically. And remember, the class is called Calculus and Analytic Geometry. So that's what we have been doing. We've been doing analytic geometry. Okay, so let's once again we reinterpret this motion in a more specific way, and moving in direction of 2, 3. How we could interpret it is as if this is the velocity. Okay, and meaning after 1 second, say we measure distance in seconds, we have after 1 second, where are we? Where are we after 1 second? The velocity. So look at it separately for the 2 dimensions. That's always you can interpret that 2, 3 is the velocity. So we move 2, say, feet horizontally per second, and we're moving 3 feet vertically per second. Okay, so that's how we understand velocity. Velocity represented as a vector, which simply indicates the different rates of motion or change of location in the horizontal and vertical direction separately. So that's it right here. We can see what has happened here. Let me go this way. So that is 2. We have moved during that second. We moved 2 units to the right, and then we also moved 3 units up. Okay, so that is the decomposition of vectors that we have talked about. But really, if it is 1 dimensional, you don't really have to think in terms of vector. It's purely in terms of changes of the 2 variables. So x changes by 2, y changes by 3. Okay, so then after 1 second, we move 2 feet here and 3 feet there. So it is then so new location is 1 plus 2 is equal to 3, and this is a 3, and the other one, 2 plus 3 is equal to 5. Okay? So in other words, new location is 3, 5. So we have two locations already, and we could certainly come up with a line for that, and in fact, a formula for that line, and in fact, we don't really have to worry about having a parametric representation, but that's exactly what we do want. We want to represent it as a parametric curve with t time being the parameter, so which means that we need, this is what we need, the location for every moment of time. We already have 1, t equal to 1. Location is, how would I call it, p of 1. This is my function, p of t. Okay, p of 1 is, as you can see, is 3, 5, but we have one more. What's the other location?
One, two.
T equals
Any?
3.
1, no, 1, 2, 1, 2 is, what's the t?
2. Because you said
0.
it's-
0. T equals 0.
I was looking at that. I'm sorry.
Okay. Yeah, and we are at 2, so in the beginning. And then all we have to do right now is just to think of a formula for this function that would satisfy these properties. It is actually enough. And we could, let's just for, since we're doing this for the first time, let's split it coordinate-wise and solve the problem separately and then reassemble. Okay, so then p of t is equal to, in fact, two functions, x of t and y of t, for functions of one variable. Well, I'm sorry, we want the real value. So these are real value functions. X is a value, a real number, y is a real value. So and then we have x of 0 is equal to 1. X of 1 is equal to 3. Okay, straight line. So that's number 1. So what's the equation? X of t straight line function x of t. X is the output this time. So at 0 is equal to 1. Let me draw it for you so that it's be more visual. So here we're at 1, and then this is t and this is x. Okay, see over there the t is missing. So now to solve the problem we actually introduce t into this. So this is one point and the other point is 1, 3 here. So what's the equation?
1 plus 2t.
1 plus 2t. Where did 2 come from? If we can trace it all the way back over here. The x coordinate, x component of the velocity. Okay? So we do the same with the with y. We have y of 0 is equal to 2, and y of 1 equal to 5. So once again, you can have a little picture here. T and y. It is 2 over here, and then it is at 5 over there. 2 over here, y, t, and 5 over here, and so this is one point, and the other point is here. Okay, so that is my line, the other line. This was one line, this is the other line. So what's the equation? 3d plus 2. Okay, and now once again I can circle this 3 to find out where this 3 came from. And so it came over there, from over here, the original direction for velocity. And 1, 2 are also recognizable. Let me circle them too. So this is 1, 1. Where is that? The 1 go? It's right here. And furthermore, this 2, okay, reappears over here. So those 4 numbers we started with, the original position 1, 2, the direction 2, 3, they all reappeared here. Now we'll see how everything works out if we reassemble this. Assemble into what? Into one function, the parametric curve. So which is obviously this one. Okay, so we're putting it in the form of a function. Okay, so it will be, I'm substituting, so I have 1 plus 2t and 2 plus 3t. That will be the answer. That is actually the answer. With this on the surface, it is the answer. Not entirely satisfactory, even though once again all these numbers are highly visible. Unfortunately, the problem with that, so it's okay, but not perfect because these numbers are not paired up. So as they were, 1 and 2 were paired up, and then 2 and 3 were paired up, and here they are split between x and y. Okay, so these are the x's. This is y. So what do I do to pair them up? I split it using the vector algebra. Okay, so now here's what I do. I can do it 1, 2 plus 2, 3 times t. So location 1, 2, I add vector 2, 3 t times. Okay, so you certainly can verify that I can add these two together, and I have this, and now you can just mark everything here as we have. So this is initial location at time t equals 0. If I plug in t equals 0, certainly that term disappears, and now indeed where I am where I'm supposed to be. And secondly, the direction of the other one. This is the velocity. Okay? So now this is better, because the problem was actually formulated in terms of vectors, and we provide the answer also in terms of vectors, or vectors and locations, rather than having incomprehensible mixture of variables over there. I could easily replace them like this. Instead of 1 plus 2t, I could have 2t plus 1, and then the structure is not revealed. And doing it this way now, it tells us what to do in general. So what do we do when we have a parametric curve, a straight line, but this time things are not specified, and then dimension could be arbitrary. So let's restate the problem. Let's start over. Yeah, let's do dimension 2 for now. Okay, so represent as a parametric curve straight line starting at how about AB? Oops. AB in the direction of UV. Okay, we already know the answer is right there looking at us. As you can see, we know what the initial location is, what the velocity or direction is, and we just assemble them in this really simple way. So, and the answer is P of t is equal to AB plus t UV. Okay? Doesn't make any difference that it's going to be three-dimensional. Okay, so I have dimension 3, I have A, B, C in the direction of V, U, D, W. What is the difference? There is no difference. We are putting in the same way the initial location followed by t times the velocity. So it will be ABC plus t U, V, W. Okay? And on. We can continue in this manner for any dimension, and we really lose the purpose of those multiple commas, multiple variables, and that is really is not meaningful anymore. So I go with the problem, not dimension, but generally I will be using just the multidimensional notation. So So represent a parametric curve as a parametric curve, the straight line starting at point P in Rn in the direction of vector B in Rn. Okay, so once again, the answer is right there. It will look exactly like that. And it will be very compact. So P of T is equal to, how about I call it Q instead? So we have confusion here. So I'll call it Q. So from a starting point Q, which have whatever the coordinate is and coordinates. And so Q plus T times D. So vector addition, or rather it's a point plus a vector, but still it produces a location. And this is certainly scalar multiplication. Okay, so that is the answer. Go back and forth whenever you see something like that. It looks more complicated than it is, but only because as long as you remember the complexity behind it, it might stop you from moving fast. But really, it looks exactly like. Let me show you. P of T is equal to let me write exactly the same thing. Now think about it. What if the dimension was 1? If the dimension was 1, you would not hesitate to, I hope, to recognize this as the equation of a straight line on the t, y, say, plane. Y and t. As you can see, so this is just to look back at calculus 1 and recognize that we are even though we have progressed dramatically forward, but the form of the equation is exactly the same. So in dimension 1, that's what a straight line will look like. I can even plot it for you. So so Q is here, and V is well, just the direction of that, like this. Okay, and V is still also visible if you want it. Will look like this. This is V. It's a bit messy. So this is V. This one is Q, so that's the starting point. You are moving. This is motion on the y-axis. So we're moving on the y-axis. T is just a variable. So you start at the point Q on the y-axis, and you're moving along the y-axis, and that is the step that you make is the length of V. Okay, so that is entirely calculus 1 problem. The slope. What's the slope of this line?
V.
The slope is V, right? So that is the meaning of the velocity fact as we expand it from dimension 1 beyond. It is the analog of the slope, and that's really not surprising if you think about it. The slope is how fast you're growing. That's how fast is the velocity is how fast the variable changes. Except here you have only moving in one direction along the y-axis, and here you're moving in simultaneously in all directions. So you have to describe your rate of change as a vector rather than as a number. But once again, appreciate the equation that looks exactly the same. So Q plus TD, that's your straight line. Okay, so the problems that you might encounter in your homework would be, say, either you were solving exactly this problem like this, only with the specific Q in B. Okay, so that is not just plug it in, and whether or not you have to simplify it or not depends on the circumstances. Another problem, it might look slightly different. For example, when you're given 2 points. So what do you do when you are given 2 points in a vector? A line from Q to R, say 2 points, and you need, this is to determine a straight line, you need to find the straight line. as a primary curve. So the inverse is the same. So what do we do? What's missing? You always trace things back. You don't want to start the whole thing analyzed from scratch. You want to trace back to the problem that we just solved. Okay, so and for this problem, we do have Q. That's taken care of. V is missing. So V is missing. So what do we do? To apply the formula, we need V. How do we find it?
Slope between Q and R.
No, not the slope, but I mean, in the one-dimensional case, it will be the slope, yeah, but in general, in an n-dimensional or just think two-dimensional case, how do we find V?
It's the displacement, the difference from.
It is the displacement. In other words, V is simply QR. Okay, so if that's what you've got, you just subtract two values, and that's so. Remember how we've done it. So Q is equal to 1, 2, 3, and R is equal to 2, 5, 1, minus 1. Then we subtract component-wise, so my QR will be equal to, I'm subtracting 1 by 1, so it's going 2 minus 1, 5 minus 2, negative 1 minus 3. Backwards, the direction sometimes matters, sometimes it does not. But if you are asked to represent the curve as a parametric curve, and you are told in which direction you go and you are, then you better not be confused between QR and RQ. So that's why I'm subtracting R from Q rather than vice versa. So, and then the answer is then 1, 3, negative 4. This is my direction vector. So we have initial location and we have the direction vector. The initial location is Q, whatever that is, and well, say I already have it. So my equation will be P of T is the initial location, which is 1, 2, 3, plus this thing multiplied by T. I put T in front because that's where we put it every time we do scalar multiplication. This is the answer. Okay, so as typically that's what the answer looks like. There might be other questions asked about it, but pretty much that's it. Okay, so the dimension might vary, but you might be asked to reassemble it again. Reassemble into 3 equations, right? So this is 3 equations, each of which is a linear equation. Okay, so that might be also the answer in the formula. So look carefully what you ask to provide. Okay, so there's really nothing else with straight lines. That's the whole thing. So let's follow Newton, and let's just move beyond straight lines and beyond why physically speaking. When we move on a straight line, what does it tell about the physics of the problem?
We're moving at constant velocity.
Constant, that's right, constant velocity, and what changes the velocity?
Oh, the acceleration is 0.
Acceleration is 0, right? Or also, if you go with Newton, beyond this, the force is 0. So when there are no forces involved, that's when you are moving at a constant speed along a straight line. So this is all forceless universe. Okay, so if there are no forces interacting or acting on objects in this universe, then you will be moving, everything will be moving on straight lines. Okay. Hypothetically, if they collide, they will go backwards also on straight lines. So now what forces are introduced, starting naturally with gravity. Gravity meaning close to the Earth. So very simple force. So now add forces. If you add forces, I'm not going to go into acceleration just yet because of the simplicity of the problem I want to face. So let's just say velocity is changing. So as you know, it is the term is, I think, uniformly accelerated motion. That's what gravity, does here, like this. It starts with 0 and then accelerates. So velocity grows or declines linearly. Okay, so and then it turns out that things don't really change a lot if we just can solve a problem of that we have solved previously, and that is from velocity. Now we need to find location, and so velocity grows linearly. It is known, and now find the location as a function of time. So grows linearly with time. Okay, so once again, velocity grows linearly with time. It is known what that function is, and we need to find the location of time. If dimension is 1, the situation is familiar. What is this arrow stands for? This arrow from velocity to location. Or you can go backwards if you like. So what's this relation? How do we find velocity from location?
The derivative.
That's the derivative. That's the derivative. So backwards. It's integration. So integrate the velocity. And well, that's predictable. If the function is linear, you integrate to get the quadratic function. So linear quadratic. So that is not unfamiliar. I just if you do it one dimension at a time, or rather one direction at a time, you can do the whole thing without vectors. But now we want to just assemble everything in vectors. So we say dimension 2, vertical and horizontal. Those are x and y, right? And the gravity naturally acts vertically. So y of t is equal to y. I'm sorry. I was talking about the velocity. So I still want to carry out that integration. So velocity is linear grows or declines linearly. It will be actually declines because we're going to choose the vertical direction, vertical up, and the gravity is actually acting down. So this is the gravity, and so it means that there will be decline. This is x. Okay, so vertical velocity is v sub y equal to, say, v naught initial velocity minus tg. Okay? And tg, and then g is time naturally, and g is the gravitational constant. Okay? So, all right, so let's integrate. Not literally integrate, but you probably already know the answer. So y of t is a quadratic function. Should be familiar.
Would just be v naught minus 1/2 t squared.
V naught minus t squared over 2g, or g in front usually. So when you integrate t, this is just a one-dimensional thing, so there's nothing tricky going on. So I don't think so v naught t, integrate v naught, what do I get? I get v naught t. I integrate t, g is just a constant, so I have g t squared over 2. and I add, in the beginning, I add 0 naught, the initial position. Initial height, or initial elevation. Okay, so that we started with the more hard part, vertical motion, the horizontal motion now. So this is vertical. We're doing horizontal now, which is simpler, because now, since we chose the directions wisely, we're gonna have no trouble with the horizontal velocity, which, what happens to the horizontal velocity?
It's constant.
Yeah, right, so the answer is nothing. So the, I guess I should have put, I can't work out notation quite properly. So it will be constant, v sub x, and so I have my answer x of t is equal to, once again, I integrated dx, I have dxt, this is supposed to be vy, I'm sorry about that. Okay, vy and dx times x naught, starting with x naught, the initial location, x naught, plus vyt. Okay, all right. So this is initial location, this is initial depth. Okay, so let's assemble it into vectors. So I have my p of t, which is made of x of t, y of t. And if I'm starting writing it out, I have x naught plus vyt, vxt. Okay, and the second one is y naught plus vyt minus gt squared over 2. Okay, so once again, this is okay, but not good enough. We want to have vectors. We want to match up things that set up the problem, and the setup of the problem is naturally the initial location and the initial velocity. Initial location, initial velocity, and the force. These are the three things. And the well, we just see it's just so revealing once we put it the right way. There is nothing wrong with this. It's quite usable, but as you can see, x's are separated from y's, and that is just not a good idea. So we already know what to do with same thing as we did with the straight line. We combine, for example, we combine the initial location. So this time location is a point. Secondly, we combine the velocity times time. That's we're moving on to the second term. So what do I get? So this is initial location. Okay, so what's the second term? Okay, let me. Right, yeah, so it will be dx dy. T, and then, well, there will be one more term. I'll just do it next time.